Hello. I'd like to welcome Cliff Click, who is a distinguished VM hacker at Azul Systems. He's been working on Hotspot for, what, about 10 years now?
Yeah.
Yeah, about 10 years. He used to work at Sun, was one of the chief designers of Hotspot there, and now he works at Azul, and he's one of the chief designers of Hotspot there. He's going to talk to us today about the monitoring tools and techniques that they use at, excuse me, that they use at Azul. Cliff.
Okay, so in case people don't know, I'm going to go through some old slides that I brought that aren't really terribly appropriate, just to talk about what Azul is and what we do and why we have the tools. And then I'm going to attempt a live demo of the tool that's unscripted by me in any way. And so after some showcasing of the basic stuff, we'll let people ask for what buttons to push, and we'll go track down stuff with the tool and see how it works. Okay, so what is Azul Systems? Like I said, these slides are a little bit inappropriate, but they're what I have at the spur of the moment. We sell a piece of hardware for running very large Java VMs, or lots and lots of small Java VMs, or sort of any mix in between. The hardware supports many hundreds of CPUs that are shared using cache-coherent shared memory, hundreds of gigabytes of heap. The CPUs are our own little custom CPU. It's a standard 3-adjust RISC. We have a bunch of hardware tweaks thrown in that make some of the stuff we do very cheap. So amongst other things we do is that we can sustain allocation rates on the order of, say, 50 gigabytes a second of allocation. That's not megabytes a second. Gigabytes a second of allocation with essentially no pauses ever. So this is concurrent GC at a very high throughput rate. And the way we do that is we have a read barrier in hardware. So like I said, I'm just going to touch lightly on what we do. It's traditionally been felt that it's too expensive to do a read barrier in software. So we did it in hardware. That hardware read barrier, I won't go into a lot of detail around it, but it basically lets us use a very simple GC algorithm that does concurrent relocation. That's sort of the big one. And that lets us run moving objects in the heap, compaction of the heap, and that kind of stuff, all entirely concurrent with the Java threads running. And that's where we get to do stuff like 50 gigabytes a second of garbage collection recovery without killing the mutator threads, without killing the running Java threads. Let me skip some of those stuff here. One of our big ticket selling items here is what we call Pauseless GC, and it's actually very short pause times. So for during the course of a day, you might see a pause on the order of somewhere between a max pause of between 100 and 200 milliseconds, although your typical pause will be 20 or 30 milliseconds, and they'll come every few minutes. You'll never get a full GC pause of 30 seconds or 10 minutes, no matter what. There's no stop the world phases needed. There's no, the individual threads only stop for brief periods of time. And we do this by running a lot of GC load on background CPUs. We have lots of CPUs, so we can do a lot of garbage collection games in the background. And then when we get into the monitoring tool, I'll show you a bunch of stuff about how the GC monitors and what we can do with this stuff. Let's see, wrong direction. Gosh, the rest of the stuff sort of doesn't matter. Like I said, the slides are old here. So let me recap real quick. We sell an appliance. It runs Java on the appliance, but it does so in a way that's very, gosh, I should start. Yeah, I'm really, unscripted talks are bad this way. OK, so we sell an appliance that runs Java, but the way it works is that you launch your Java VM on your running, let's get this up while we're looking here. You run your Java VM on your existing CPU, and we just ship the bytecodes over to our appliance, run the Java there, ship the results back. What's running on your original machine is nothing more than like a Cisco router, or we call it a proxy. It's just a packet forwarder. It takes the I/O, ships it over to our box. We do all the work there, ship the answers back. So in this case, this box that we're showing here is a standard Linux machine. It's a 2-CPU Intel, looks like totally normal blade. I've just run a 64 warehouse JBB because I've been dorking with command line flags here. I've specified for no good reason a 200 gigabyte heap. So here's mem commit of 200 gigabytes. This is going to be 64 warehouses and run for like 2 minutes. Not very exciting. Up top, oh, JBB. I'm sorry. JBB is a very standard Java benchmark. The way you're supposed to run it is run it with as many many threads, many warehouses doing work as you have CPUs. What I have up top is a perf bar showing a 768 CPU Azul machine, which if I were to run this with 768 warehouses would take an hour to get set up. So I don't want to do that. So I'm going to run it with like 64 because I can do that in a few minutes. And in theory, what you're really supposed to do is run adding one warehouse until you double the peak CPUs, and then you look at the tail off between max and twice max or whatever. But it takes about a couple days to run an official JBB score on our big box. So this is instead, I'm just running, just loading the warehouses. We'll take off at 64. Up here, there's going to be one CPU is actually doing the loading, and the rest are doing background GC cycles periodically, and there's a bunch of compiler threads thrown in there that I'll show you in a minute when I get to the monitoring tool. But this is a perf bar then. Green is a CPU busy, red is kernel, and it runs off to the right of the screen. Let's see if I can flip over here. This is my bad connection. There you go. OK, there's the right-hand side. That's the other half of the perf bar. So you can see it's just too big to show everything. Let's go share the memory thing. We'll just get back to it. OK, so mostly I don't care about that, except I'm going to start here. Take off here any second. OK, we're getting bad VPN lag here. Oh, it's trying to go. Somewhere in here, it's oh no, we're getting bad. You can see it's going for like the 64 CPUs all at once, and then they drop down, and VPN's giving me a 1 second peak. So let's skip that for a minute. And let me pull up this other guy. We'll come back around to this guy in a second here. So the tool that I'm going to talk about is our, actually, let's go to here. This is our RTPM, Real-Time Profile Management, whatever. It's an acronym du jour. And this is a Java web browser hooked into the running JVM. So you can attach any web browser into the existing JVM. And we'll look at all the stuff I can do while the JVM's running. None of the stuff I do has any overhead on the JVM. And that's mostly because JVMs do collect a ton of internal information. And then they don't typically export it. We've just drug most of that information out. We found this very useful, so we kept adding things that we could drag out that didn't cost us anything. And in the end, we have a whole lot of cool stuff we can get out of a running JVM without any interesting overhead on the running JVM. So somewhere back over here, on the other window you can't see here, down below, I have an old JBoss window. And I have, oh, by the way, I am running the local internal engineering build of things. So this is live in a lot of ways. Let me run Grinder on this guy. So this is JBoss with Grinder. The JBoss window's up here is already running. I've just fired off a Grinder load. And then here is my RTPM startup window. I have the command line for JBoss. This is me calling out my version of Java on the Linux side. And then some JBoss arguments. Use locked collections is how we work around bugs in JBoss where they fail to properly unlock Java, the unsynchronized Java collections. And then other stuff. I have, say for instance, all the hotspot internal flags I can look at. There's no end of them here. Here's C1 and C2. You'll hear me talk about C1 and C2 a lot. That's server and the dash client compiler. You guys know anything about hotspot and dash server and dash client compilers? Some people. So dash client's the lightweight, fast compiler. Dash server is the heavyweight, slow compiler. We have it in a tiered configuration. We run client. We profile using client compiler and recompile using the server compiler, using the statistics gathered from the client compiler. I can look at the ticks. I'm running JBoss. Most of them are caught between GC and fill and stack trace because I'm running a very small heap on GC. So I'm doing endless GC cycles in the background. If I go find somebody who's actually got some code compiled here, I can get disassembled assembly language code with ticks, profiling ticks on the left. and where in memory, and here's the actual machine instructions. This came out of the heavyweight server compiler JIT. That's our internal assembly language for this particular giant method. Sun, IO, UTF, encode, whatever.
This is the code for that method, yes?
This is the code that is generated by the heavyweight JIT for that method, yeah.
I mean, so the numbers on the side percentage is the percentage of the time that you spent
in this method. That's
in this method. Okay, so the most expensive thing to do in this method is probably not the code.
yeah, which probably means that we bail out real quick out of the method. You came in, you took some stall cycles getting into the method, and then you did a little bit of work, and they're all spread out. There you go. Okay, so there's lots of ticks down in here. We come in here a long time. If I were to guess, I guess there's some loop going on here that's doing something. UTF encode, I'm totally going to guess here, but this looks a whole lot like load a character, store a byte, and search and loop. So I suspect he's spinning through a Java string, pulling 16-bit characters out, encoding them in 8-bit bytes, writing them back out to a byte array somewhere, and he's looking for some Terminator character. That's just a guess, based on the name and the kind of coding style I see here. Big unrolled loop, and on and on and on it goes. So here's push frame, R12, resolve patch call. That's a standard function call. Resolve and patch is an unresolved function call. Let's see if I got a resolved function call in here. I don't. It's all inline unrolled loop. Oh well. Caller info. Car set encoder gets called mostly by string.encoding, which gets called by subnet double protocol, which gets called by, and so on and so forth. So I have call path and annotated with the ticks. That's the compiler profiling stuff there. Let me roll down here. Let's see here. So here's the running threads. I just clicked on the threads list. Here's all my threads that are currently running this JBoss. Most of them are probably not doing a whole lot. This guy's doing something. He was at the time I looked. This is completely live, so I can refresh and see if things change. See nothing change. Oh, he did change. He switched to the lock. I get a stack trace on the live thread. He's in the middle of fill and stack trace. Well, that's where all my time is going. OK, that's fine. If I look down in here and say, so what does he get? A legal argument section calling date.parse. Here's date.parse as the method itself. Here's the compiled code for it. It's not really what I want. I want to know why he failed. So whatever. Here's the code for date parse. I'd really like to know why he failed and start storing exceptions. So what I really want to do is see if I can get a medium stack trace. So he's going to have moved. So medium stack trace is breakout of every bit of thing. The server compiler guy, that's the C2, won't have a whole lot of information here because he's optimized it away. Let's see here. Here is the this pointer for this frame. So we start at the top. We're stuck on a socket write. Came from Java net socket output stream write, which came from this write call, which came from internal output buffer dot blah, 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 which came from, so on and so forth. Somewhere down in here, I start seeing stuff like, here's a this pointer. It has an actual object. Here is a local variable, which has a 1. It's named real flush at the Java level, and so on. I can drill in on an object. Here is this instance of this object. It's got an array of characters, which is null. It's got a 1,000-byte size write buffer thing. It's got a field called lock. It's got whatever things it has. I can drill in on each of these other things, too. Oh, my head's spinning doing that. OK, so let me come back around here. Let's pick a new top-level thing. Here's monitors. So what's up here at monitors? Monitors is their hot locks, contended locks. Compile lock, code cache lock, these are internal VM locks, but this is a Java-level lock. If I drill in on him, I can see here is a typical blocking call to that lock. So that is my highest level hot lock. And the reason I can't keep more than a few CPUs busy running this version of JBoss is because this lock is contended. I have, there's other locks in here. So this is actually not a very big example. I need to get something with more threads and more locks. Here's freemarker.cache. 2/3 of the time you come in on somebody's get template call, and you take this lock, cached at MRU cache storage, and block. And 1/3 of the time you come in on this call. It's interesting. Memory, let's drill in here real quick. So I've given myself a 4 GB heap, currently using only 500 megs. I've run 1,000 GC cycles since I started JBoss a couple hours ago. If I get a GC summary, it'll see summary of the last 50 cycles, so the last, there you go, last 20 minutes. Lots of stuff, including allocation rate and the size of the heaps. So here is doing like 30 megs a second on this JBoss. There have been no thread delays. Let's see what else here. There have been pauses. The largest pause in the last 20 minutes has been 73 milliseconds. And that's in the young gen. If I go to the old gen collection, the largest pause has been 16 milliseconds, and so forth. Allocated over all time, I can see I've had 2 gigabytes of car arrays allocated over all time and 500 megabytes of byte arrays. But a more interesting one here is, yeah, that's all things. So let me be clear here. I intend this to be a live demo, so people ask questions. I'm going to steer around and drive and look at stuff and poke at it. I can run different applications. I don't have a huge selection, but I can, you know, if I have it, I'll run it. I have a lot of the random weenie Java benchmarks floating around. JBoss is sort of the more realistic thing I have here. And then, you know, really it's sort of like, how would you use this to go do something interesting? So for instance, here's what's currently live in my heap. I got 63 megabytes worth of byte arrays. And if I drill down in the byte arrays, I have points to information. I see that 40 megabytes of that comes out of jar files, and another 15 megs out of zip files. So this is my class files. I've loaded my class files as byte arrays at the Java level. So that's not going away. It's not going to get smaller or bigger. There's nothing I can do about it without loading the class file. So it's maybe not interesting to look at byte array. But if I look at com.netspective.whatever, I have 50 megabytes live in my heap of query entry log things, of which most are pointed to from Java-lang object array. So if I come down here to Java-lang object array, I see that most of these come out of array list, and some are rooted. That's what unknown is. They're currently live on somebody's stack. If I could jump to array list, where'd array list go? I see that most of the array lists come out of, well, they come out of com.netspective.something. So somebody's making piles of array lists and hanging on to them. Somewhere in JBoss and all this netspective stuff are a pile of array lists being hung on to that hang on to a huge ton of com.netspective.axiom.whatever it is. So I don't know anything about JBoss, but I can tell you where the memory goes and, you know, who's pointing to whom buried there in the heap. Let's see, the compilers at this point are going to be totally idle. Yeah, the compilers are idle. And settings is not going to have anything interesting. Yeah, a couple on-off flags for things that actually cost. So pretty much everything I can show you here, let's go to I/O for a second, is all gathered sort of free of charge from the point of view of the VM. It doesn't slow it down at all. And it's always available. It's always on. You attach with the VM, you attach with the browser, and you start surfing around. This would be true on like a production VM that was a week old. You know, you had a weird crash or performance anomaly on your running VM. If it's still up and running, you can attach to it and look at it. So one of the things I did here is I looked, I see, oh, I got 25 million calls to stat. And 15 million calls to stat mode. And I can see how often they're coming in. Where do we go here? The moving rate, there's like 10,000 calls a minute of stat. The appliance is, you know, running the bytecodes on its side, and the proxy is running on the standard Linux or Solaris or whatever OS you have on your side. So the appliance really has to do a caching of like standard I/O stuff in order to get performance. Otherwise, it's an RPC call to and from the proxy. So he has a cache for lots of stuff, including like a name cache, and so I can get stats on how well the name cache is doing, who's hitting and missing the name cache. I can take a look at like, here's open sockets. I've got a bunch of sockets open for exactly this browser right here. There's another socket open. I don't know where that one came from. And then JBoss opens a bunch of sockets because he's listening for the grinder process, which is throwing transactions at JBoss. Get open file handles. A lot of jar files are open. 100 lines of jar files. What else is open here as an open file? Oh, here you go. Local database. There's a log files open too. Yeah.
Does this aggregate the statistics of all of them?
No. So let's go back over here. Let's see, where did this guy, here we go. Let's kill this guy. So I'm going to turn on some engineering flags here to make my life easier. Except that I can't type. And oh, VPN, come back, come back, come back. Oh, God. Oh, man. Oh, no. This is disastrous. I'm picking a different port number. If you were doing this in production, you'd have the ports come out auto-configured on launch. But I'm running an engineering machine on an engineering setup, and we don't have the management stuff running on this guy. So in fact, I'm going to, yeah, you can't see. I can't see. OK, look, it looks good. OK, maybe, assuming that the typing wasn't so bad. Yeah, that looks bad. Yeah, you can see.
Now you've got one running on 1, 2, 3, 4.
1, 2, 3, 5. I'm aiming to get one on 1, 2, 3, 4 and 1, 2, 3, 5. Except I probably can't spell SWX 2021 1, 2, 3, 4. SWX 2021 1, 2, 3, 5. Did I mistype something here? Or did I fail to open? Oh, come on. Why did this work and this one? I know, dangers of the live demo. So the answer is that I can open up as many as I want. I mean, every process is its own thing.
Right, but yeah, I mean, my thought was, you know, if you've got a sort of, you know, I've got 760 processors and I'm running 768 PMs, well, maybe you don't.
Oh, you want to aggregate across the whole thing. So, right, so if you go to the management console thing, which I wonder if I can get up here, he will aggregate across all of them. So this is definitely me being unscripted because I don't have the passwords put in here. So these are two different Linux boxes launching against the same appliance. OK, so this is, in theory, going to be, OK, this is startup of JBB. So spec.jbb.main calls do it, calls run warehouse, calls yada, 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 yada. And up and we go. We see he's busy running. I'm sorry? How many? Yeah. The big appliance, you know, 100, 200. I don't know in production of people that maybe run more than 100, but I don't know. Some of the guys have filled up. Kind of Suisse has got a couple of big boxes really full. If you use a developer box that's going to be like a quarter that size, so about 200 CPUs, you can expect to have, say, 20 to 30 JVMs on there really without any trouble, you know, without knocking heads on each other and running out of resources. So at this point, let me start taking questions from the audience about what to go look at here. Are people interested? Yeah.
So do you have information about indirect virtual calls?
Can you speak up or use the mic?
Do you have information about virtual calls?
Do I have information about virtual calls?
And how many targets they have?
Right. So Hotspot by default heavily optimizes virtual calls, and without Azul doing anything special there. That's just Hotspot. Most virtual calls, in fact, call a single target, and the runtime, the compiler knows it, and they prove it, and then they make that go to a single target, and they inline. And then you won't actually see the call at all. It'll just be gone. For an interesting fraction of calls, they aren't able to inline, but they are able to show that there's a single, very common target, in which case they do what's called an inline cache. It's a one-entry cache built right in the code where the key is the expected target and the value is a subroutine call to that target. That will just be inlined in the code. If you go to the profiling information here, let me go do this before my JBB runs out. If I go look at profiling information here, not drug out properly, because this is an engineering build, is a list of all the targets that we went to. But the server compiler knows what those targets are, although the display coming out here is not showing it. I've turned off funny flags for that. And that's just, we're in the mid-release cycle kind of thing. But that information is certainly in the machine, and it's intended to be drug out. But the usual answer here is you have a single target, and if you go look at the server compiler's code, he will have inlined that call. You won't ever see the call. It'll just be part of the code.
And you can go look at the server.
I can go look at the code here. So I don't know which version I got till I jump into the assembly I got here. And in fact, I got server code. And the server code is very short. And there were subroutine calls in the bytecodes, but there are no subroutine calls in here till they get down to these things called uncommon trap. Those are paths where the server compiler cut off compilation because profiling data revealed you never went down that path. So he inlined all the calls that were to be had in the main piece of the code here. And the last thing he's going to do somewhere down here is jump to a return, if I can find one buried in here. 138, here it is. So he's got a loop going on. Here's a branch to A018. From here to here is a loop. And then somewhere near here, he bails out of the loop and just does a store and return. And there's no function calls now. So probably had a loop around some little byte parsing thing. He inlined all those function calls and disappeared them. And so what they are doesn't matter. I'm going to take the guy at the mic first. It exists, but it doesn't work. That's cool. Surely you want the green light instead. Try it again. Maybe it's got good.
Are we getting? Ah, we are. So systems often have both short-term and long-term behaviors where things will happen, once every few hours or something like that. Do you have ways of tying into things like that so you can look and see, well, show me what happens when I arrive here as a result of an uncommon event versus a common event or something like that?
So the management tool, which I have failed to get the password for, has a lot of that kind of stuff built in, including trend line diagrams that are scrolling by time things. So you can watch heap growth events and the like that span hours and days. This tool is using Git, HTTP Git. And you could certainly arrange to have somebody running Gits against a running JVM on a regular basis if you wanted to write your own version of a tool and extract out what was going on, and arrange to have your own profiling bits there. So there's nothing magic here. You can do URL hacking and go get what you want out of the VM. And because there's security issues and we sell a lot to banks, there's in fact password games that have to be played if you turn on all the right, we want things to be secure mode. But if you're inside your own firewall, then you just do URL hacking, you can get what you want out of it.
Can you get from the assembly language to the bytecodes from which it was derived, and from that to the original Java source code?
So not to the source code. I don't have source. We have debated doing stuff like JADing bytecodes, but that's sort of, gauche or something. Yeah. So here is the client compiler's version of. Come back. Oh no, we're done.
You should add that this is not your benchmark. This is something that you only that you have a jar for, and you don't actually have the source for it. If you have the source for it, you can presumably.
In fact, you can get the source for it, but they haven't been compiled by it. And in this case, I am looking at shutdown errors on my exciting version of the VM, which I have bigly hacked locking, and I expected shutdown errors, which is annoying, which is why we hung there. Let me, let's just relaunch, see what happens here. So what I was trying to show there is the assembly and the bytecodes are side by side. I mean, I'll flip between them here in a second. Let me bring this guy back up. So let's just get coming fresh. Okay, here we go. Ticks, create a random string. So here's the assembly with performance counter ticks. Here is client compiler bytecodes. So get static 8, iload 2, AA load, These are standard bytecodes. Invoke static of this function call, and so on and so forth. See, what's this guy? So here is that call. I just jumped to the version of random here, which is random.nextInt, random.next, and do a little math. There's an add, remainder, and return the value. So it's it's random. It's been inline, so there's no assembly for that routine. The server compiler, he doesn't have the profiling data on him, so I know these are all going to be 0. But he will say he got inlined into the caller. So at this point, the server compiler code for this guy has been inlined. This call got inlined. And oh, here we go. This thing's been invoked 5,000 times. There's a back edge in the middle worth 134,000 times. Somewhere here he's spinning in a loop. Let's see if I can find it. Reached 130,000 times, reached. This is, I returned to this invoke static. So here's the client compiler inline invoke static. Here's the client at depth 1. Here's the client compiler at depth 2. So the problem with looking at bytecodes is because of you're interested in the inlining. And the client compiler and the server compiler are going to do different levels of inlining. And I'm only going to get collect profile info on the client compiler's inlining levels. It's just sort of the nature of the beast. But yeah, I am looking at the bytecodes here, and I'm looking at the assembly here. So does that answer your question?
Yeah, if I, poking around here, I discovered that there was a bug.
Yeah.
I really want to be able to get to the source code so I can fix the bug.
Right. So yeah, the hard part there is you'd have to give me the path to the source code at the time you launch the VM or at the time you run the browser here. We have the line number tables and all, but I don't have any good way to bring out line numbers in any interesting way unless I have a path to your source code as well. It's something we could do. It's actually an interesting idea. Oh, here we go. Here's JBB running now. Here's 64 threads all busy hammering away, doing whatever they're doing. Transaction manager.go calls, and so on. And here's a lock. Let's see if I got a hot lock display. It looks a little better. Yeah, there are no interesting locks in JBB. These are all internal VM locks. Yeah, I can't see it because it's an internal VM lock. Here, somebody's locking an object, but very, very rarely. Transaction manager go occasionally locks some object. People interested in looking at other stuff here, I/O or GC cycles, or?
You said this comes with basically with no cost in your VM.
Yeah.
I didn't quite hear out how much of this is in the standard hotspot VM and how much of that is custom.
So right. So about a third of what you see is computed inside a standard hotspot VM, but it's not brought out in any convenient way. So hotspot internally will profile, and he will internally have sort of the high-level profile bits available to him about what methods are hot. And he'll have some amount of the GC cycle time stuff available to him for his GC heuristic trackings. Hotspot right now doesn't ship with a tiered system, so you don't get a server-client split. You get profiling in the interpreter and the server side, or essentially no profiling, and then you run the client. Beyond that, that information's inconvenient to get for them, that we've done custom hacks for. So for instance, per thread dumps are something that's inconvenient to get in the existing hotspot. We've completely redone how we stop and start and run threads. And that makes it easy for us to pick an individual thread, get a stack trace, very cheap, get a stack trace and have it take off and keep going. That's hard to do in the existing hotspot implementation. The garbage collector doesn't do points to information in the existing hotspot. That's something we hacked in. We require a major GC hack to get at that. The tick profiling information, as far as I know, that's not easily available in hotspot. They do performance counting, which is different from, we do both the hardware tick counters and the software counting and the profiling. So you can't get at the ticks like I can with the code. Now I can spit out the code as a hotspot engineer on an existing hotspot VM by using the right magic flags, but I can't tell you where on the code what piece of it's hot. The hot locks thing, again, I don't know that that's convenient to get out of an existing hotspot. I haven't looked at what Sun's been doing. I know they've been thinking about that stuff for a while. But we hacked our locking idioms a fair amount to make it cheap to gather that information. And then once you get it gathered, of course, you want to bring it out so we can look at it. So a lot of what I'm showing off here require deep VM hacks that I don't believe Sun has done.
Sort of related to the source code question, any given sequence of instructions may be derived from a bunch of different sources, all sort of interleaved. Is there some way to look at a sequence and say, oh, you know, these memory references are coming from that module, and those ALU operations are...
You know, since I'm an old-time compiler hack, I can often look at the source code and the generated code and tell you what went to what. But that's not going to help you unless you're a compiler hack. It's hard to do. OK, the VMs, the program ran to a halt here. Let's try again. The hard part with that one is the level of optimization is such that there's not a very direct correlation between one and the next, right? So it's going to be really hard for me to say or explain to you how I got to where I'm at from where I began with, unless it's very simple. If I take a very simple loop, you can look at the code, you can guess, oh, I know what that's doing. But as you add complexity and you start inlining, it gets big, how are you going to make heads or tails of it? I don't know. You want aggregate information. You want to come back out and say, OK, I'm calling whatever dot random 1,000 times a second. Ooh, wrong thing. Let's try this one. I'm calling whatever stock init stock 1 billion times a second. Why am I doing that? And then figure out from there what's going on. You can go to the threads and get poor man's profiling by simply drilling on a thread over and over again. So here's integer.value of inside load init table. Okay, well, if I run a few thread dumps here and nothing changes, this is my common path on the main thread. Okay, it's the startup time. Main's busy constructing 64 warehouses. When it takes off and main goes idle, I can look at the worker threads and see what they're doing that way. I can get field names out of the generated code when they're actually available. So here's compiler 2. That's the server compiler. He knows that what at the Java local Java local 1 bytecode level is hash map value iterator. So I can tell you what the Java locals are if I went back to the bytecodes. Where's my field names? Here's the interpreter. It's a giant frames there. Oh, 34 entries. Oh, here's a string. Huh. Another string, results.spec.jbb.whatever. So yeah, it's always the case that you have the difficulty of looking at code and figuring out where all the parts came from. This case, integer.value is probably pretty quick. These two instructions I happen to know are how we're doing tracking of lifetimes of generated code. And then here's an allocation idiom. New TLab, there's a setup for it. And here is integer.init, not inlined. And then a branch to return. Does that answer what goes on there? It's hard to say, right? If you knew what your code was supposed to be doing, you can usually tell looking at the generated code. Or at least I can. That one's tougher.
Yeah, it's sometimes useful just to know this
set
of instructions as a result of those 5.
I know what you're asking for.
Yeah.
There's a lot of instruction scheduling going on and a lot of interleaving of one thing or another. And so it all kind of gets blended together and it becomes really hard to tell who's doing what for where. So here's a pile of loads. Here's the LVB, by the way, is our read barrier instruction. So I've done a load 24 offsetted from register 5. Register 5 was the register 0. So this pointer. I loaded a field from the this pointer, field offset 24. The compiler knows what that field name is, but I don't have that brought out in any way. He doesn't track the name, but he knows at compile time. Same thing here. I loaded a different field. I ran the 2 read barriers, but they got scheduled, so the loads overlapped. So there's some scheduling going on there. And as I go further down the line, I'll see cases where the scheduling will be sort of egregious. It'll be hundreds of instructions apart between pieces of some inline function, and it'll become really hard to track. I've looked at such information. What I'm getting around to is I've looked at that information in the past. It's less useful than you think.
unrelated question. Very often with sophisticated optimizations, if the source code does something a little bit wrong, you won't get to take advantage of those optimizations. And so there can be cliffs in the performance of the code if you introduce some new piece of functionality, all of a sudden things get worse. Do you have any aids to try and diagnose those sorts of problems?
No. As a compiler hack, I know it when I see it, but not how to explain it to somebody else. If you turn on or off your new thing, you can often see where the time went and didn't go, right? But you don't know why the optimization didn't kick in. That one's harder to do. One of the things that does happen in this kind of environment is that we're looking for optimizations that are very robust, because people aren't expected to be experts and you're not expected to go tune the heck out of things either. So we really need the optimizations to work when they work and not when they don't, to try and avoid the cliffs that you're talking about. Now, having said that, there's a very obvious set of cliffs that show up in micro benchmarks that people fall over all the time, and I don't have a good answer for, although I can tell you exactly how they appear. And that's the one where you run a hot loop 1,000,000 times. The body of the loop consists of a function call to a particular target. The first time you run that loop, you're going to one target. The compiler knows it. And he says, aha, I'll inline. And he inlines, and he unrolls, and he strips the loop clean, and you get some really fast number. The next time you call that loop, you go to a different target. Well, now that one function call ends up going to 2 different targets, and the compiler refuses to inline now. And at that point, you lose all this great optimization. So in this kind of a thing, you run the loop once, the first target's fast, and the second one's slow. And it looks like the second function call is the slow one. But if you reverse the order of the calls, again, the second function call will be slow, but it'll be the other function call. So it's unrelated to the function call or target. It's related to the fact that you went to 2 targets. First target is fast. 2 or more targets is slow. And that one's a tricky one to get right when you're writing micro benchmarks. Other than that, the optimizations here are pretty darn robust. Like the inlining, we inline very heavily. You won't kill inlining by adding one more layer of indirection. We'll continue to inline sufficiently that you get the good performance benefits out of inlining. That has, by the way, been one of the issues I've had with other compilers in the past, where at some point you made the function a little bit too big, and he quits inlining from that point to the end, even trivial things like accessor functions. And then performance definitely falls off a cliff. But our inlining heuristics, they're very robust against that kind of stuff. That's, by the way, just totally a hotspot general thing. That's nothing to do with Azul's gear or not. So we have a lot of stunned looks back there. No one's, let's see here. Are people interested in looking at more at the GC side of things or at the I/O stats I've picked up here? I guess probably this guy's toast again. Yeah, he's run to the end and killed himself.
So do you have a way to see how many cycles are spent in C1 compiled code versus C2 compiled code?
Yeah, but it's not. The answer is always not much in C1.
Okay.
Because as soon as you get much in C1, it triggers a C2.
Right.
So if you have a very short runtime program, then yeah, you'll spend an interesting fraction of that short amount in C1, because that's all the further it goes. But as soon as the runtime starts to stretch out from seconds to minutes, it's all in C2 code.
So you don't have any applications that have a large enough method footprint that they just spend a lot of time in the JIT and in C1 code? Or other things that would cause code, C2 compiled code to get invalidated and recompiled?
Well, we do see code where C2 gets invalidated and then recompiles. But in the end, you end up in C2 code again after the invalidation go around. Do people know what I'm talking about there? The server compiler makes these very aggressive optimizations. And as part of them, he will make assumptions that so far have held true. Like, I've never seen this value be null before. So instead of putting an explicit null check, which the Java semantics required me to test for null here, I'll put an implicit null check where I simply load through it as a memory reference. And if I get the hardware trap that says I took a null memory reference, then I tested for null. But the recovery from that's painful, it's slow. So I don't want to do that very often. So if I've never seen a null, I'll go ahead and emit the fast version. And if that holds true, then I win. I don't have to do a branch on null test, right? But if it ever fails, then I have to do the recovery. It's expensive. Then I recompile that method, knowing that I've seen a null now, and I get rid of the null test. So the C2, the server compiler, may go a couple go-rounds compiling the same method as it discovers the boundary, the profile of what's typically taken in the execution of your program. Having said that, after a few minutes of a phase change in your program, startup to steady state or steady state 1 to steady state 2, just typically after a few minutes, you're all in C2 code. And that will show up in the tick profiler. You'll click on the hot things. There'll be C1 methods for a while, and then the hot things will be all C2 methods.
So do you have any story about how real customers use the tool to resolve their real issues?
Yeah. So see how far I can go here. So a lot of them, some of the issues show up in how you scale. So people are trying to run more threads. So I showed you JBoss is running basically 4 CPUs, and he's choked on that lock. Okay, now that you know he's choked on that lock, you can go fix it. And figure out how you're going to stripe the lock, or you're going to shorten the hold time, or change how you're doing to get rid of the lock. And then you go back and run it again. Okay, now you're using 8 threads, let's say, and you're on a different lock. And you go find that lock, and now you can go fix it, and so on. And then you discover you're out of threads. All the threads are busy, but your thread pool's too small. Right? You can tell that. You can go look at your threads list. They're all running. None of them are blocked. But your throughput's limited by, count of threads. Okay, increase the size of your thread pool, and so on. That's sort of one obvious way. Another thing that happens is people will use our garbage collector to fix egregious GC pause time issues that they have, but usually it just means they made the problem go away. So we have a lot of profiling data on garbage collection because we have people who are very interested in knowing that they're not seeing big pauses. They have soft real-time issues. But that's usually not an issue for us. You can tune the GC if you want to within a hair breadth of killing it. But it's nothing like the kind of profiling that typically goes on a regular VM. If someone's up against a 2 gig limit or a 4 gig limit or whatever the Linux limit is, usually they've profiled extremely heavily on the garbage collector. A dozen flags, 50 flags, 100 GC flags. I've seen huge command lines you wouldn't believe. All those problems typically go away. So they are very interested in the GC information, but it's not a problem at that point. We have had people stare at the I/O stuff, figuring out that they are doing a lot of I/O. As you scale the thing up, of course, scale your program up, you get different bottlenecks. And at some point, the logging that was cheap when you were running on 4 and 8 cores becomes the bottleneck when you're running 16, 32, whatever. And you find that out by looking at the I/O side and saying, oh my God, I'm coughing up a megabyte a second of log file, or 20 megabytes a second, or something like that. I've got examples where it was literally a gigabyte a second of log file, and that was the block, that was the the bottleneck. Let's see here. People doing the thread dumps, not the detailed ones, but the just one line per function call. We're looking at how a thread got here, what the heck are you doing here, kind of things. How did this thread get in here? It's usually a concurrency race issue. They didn't understand how they had a race error somehow, and the problem was they have 2 threads going in, one's modifying, one's reading, and they thought it was a single-threaded piece of code. And they get a stack dump back out. Now they know why. So for me personally, I use a lot of the code-generated side of things to do compiler hacks for performance. The only one I did was this is do I do client hacks for individual client machine individual client targets. The only hack I did was prefetching simple strided loops, long-running simple strided loops, which has broad applicability. Somebody walking down a giant array, we'll prefetch all the way down. Based on that, we get the stream benchmark. We have a Java version of stream benchmark. We get like 85 gigabytes a second sustained memory bandwidth, which puts us in the top 20 supercomputer list. It's an interesting thing. And I didn't do any hack for that one. I did this other hack for this other customer, and oh, look, stream got huge. Yeah, that's it. No, I don't do any other hacks. The hacks are all generic. It's actually 3 now. So I think we're about on target here.
Is there any other questions?
You got another one? Go for it.
Classic Fortran code is very, very predictable, and Java is originally envisioned was this sort of take the world as a stew pot and stir kind of thing. And I wonder in practice when people solve this is sort of a follow-on, when people solve their performance problems and then change their systems in some way, how dynamic is the performance behavior? If they solve their performance problem, do they come back a week later and say, oops, we have a performance problem again? Or do fixes tend to be pretty stable?
I think the fixes tend to be stable. Because the expectation is, when you say about a performance problem, it's usually, I need to get some increment more. And that's going to be reasonably stable over time. If the answer is, I need to get the most I can ever get, and more is always better, then I have a different kind of performance problem, right? And that's a different beast. But if I'm not meeting my current SLA, my service level objectives of 95% of my transactions complete in a second, and I'm not far off, probably a few fixes and I'll be on, and then I'll be there, and that'll be it. It'll be done. And that will be stable. That's one of the reasons that people leave these servers up in the server room forever. Once they got it, it's like, hands off, don't touch. And one of the things that's true for us that's a little more difficult for other folks is that we're very stable under load because we typically have a spare CPU for every thread that's runnable. So as you pile on threads during peak load, they all get to run. And then you don't have issues where the guy holding the lock gets context switched out by yet another runnable thread, and there's not enough CPUs to go around. And so eventually you have to context switch back to let that guy finish up and get his lock out. And there's a whole lot of stability and performance that comes out under load there. But that's just the wonder of having extra cores to throw around.
Thank you.
Yep.